Okay, so let's look at logistics regression. Let me share my screen. Okay, I'm going to choose this one. Um, all right, so the screen is being shared right now. So let's pull it up and look at what logistics regression is all about. Follow the tutorial. In terms of regression in itself, is actually looking at two variables and the relationship that they have. So if one of the variables is dependent on the other, the dependent is called a dependent variable, and it is dependent on independent variable. So when we're talking of regression, we are looking at how two variables relate. Now, this relationship, it can be simple linear, can be multiple linear, and it can be logistics. Now, in terms of simple linear, you are looking at just two variables and their relationship, one being dependent, the other one being independent, or one being predictor, the other one being the response. Now, if you are looking at multiple linear, you are looking at more than one variable that has an influence on one single variable. So you have one dependent variable with many independent variables, or you have one response with many predictors. Now, if you are looking at logistic regression, it can be a simple, it can be multiple linear. But in the case of logistics, the dependent variable always have a binary outcome, either present or absent, yes or no, male or female, dead or alive, healthy or unhealthy, all those things where you have binary outcome is either this or that is what we call the logistics regression. So let's look at how this is being done in R. In R, there are two ways. There are two ways. There's a function called lm and then lglm. The glm is a general linear model. So the general linear model, it takes all types of model. But when you specify, I don't know if I have the syntax here, time series analysis. Okay, so this is logistic regression. And so this is the syntax that I have here. I'm going to copy that to my R environment. And so this is where we are. So if I come here, I'm just going to paste this and look at the syntax. Maybe I should comment that out and pull it to the center here. So here, if we are looking at logistics regression, this is the function that I'm talking about, general linear model. But in that case, you have the formula establishes the relationship between the variables I spoke about. Where are you getting the data from? This is where the data you are picking it from. And of course, the family will specify whether you are dealing with a binary outcome or binomial outcome or whatsoever. Immediately you specify the family as binomial, it means you are dealing with a logistics regression. Now, let's check something. We have a data set here called the empty cars. The empty car is actually a car collection, maybe, and you guys by now should know that the tutorial, this is how it works. In any case, let me be sure that I am sharing my screen and then, okay. And so by now, you guys should know that if you have a package and you want to have any information about the package, just put a question mark and run the package. And then, so you see the empty cars here. So you can look at every information about the cars, and this is the syntax of all of them. Now you can check the structure of the empty cars as a data, and then you get to know that some of them have binary. So this one is the VS. If let's start from here, you have MPG, that's the miles per gallon. You have the cylinder size, you have the piston displacement, you have the horsepower, have the draft, that's the weight of the weight of the car. Let me put it that way. Or the weight of the shaft. Then we also have the weight of the car itself. And then we have the QSEC. If you want to know the definition of all the variables we have here, come and look at them here. The QSEC, we are talking about miles, what the quarter mile time. And then we also have the VS, that's the engine shape. Like you have the V-shaped engine and we have the straight engine. Like, and then this is how you look at it. We have AM, that's the transmission type. You have automatic and what is manual, the gear system, number of gears, and then a cab, that's the number of carburetors. So that's all that we have here. If you now come and look at it, you see that some of them have binary. So the 0 here means the car is either a V shape, and 1 means is either a straight, the engine is a straight engine. The transmission is also a binary. So you notice that we have either automatic car or a manual car. The gearing system and whatsoever, they are all inside. So if you are not going to do your logistics regression using this, you should know that your dependent variable will be any of these I have here. Those that have the binary output will definitely be your dependent variable or your response variable. And then your independent variables can be the rest that we have here. So let's go ahead and then try and look at how to be able to do that. All these things are things that you can just check to be able to know how the data is. You can check the tail, you can catch a glimpse of the data. And then I decided to pack this. I selected some few of them from the columns. By now you should know this under subsetting of a data frame. It's actually a data frame. When we look at the structure, you saw that it's a data frame. As you can see here, it's a data frame of 32 observations, 11 variables. So we go ahead and then we try and look at a few of them. So I selected a few of the variables. I'm not interested in all of them. I'm looking at only the transmission type, the cylinder head, the horsepower, and the weight of the car. And so I pack those variables into a new a variable called my inputs. And so it's the same thing I have on top here. Now, when I want to do a logistic regression of the AM. So, and this is the syntax I've already said, as you can see here. Let me drag this to the other side. So when we do that, I can actually run this. So the formula says that we are looking at the transmission type, which is a binary, as our response variable, being explained by the cylinder type of the car, the horsepower of the car, and then the weight of the car. So if you run that, we have our data, or we have our model, which is now called this. This is the model that we are talking about. That's the am.data. Now we can print the summary of our model and then look at what it means. In terms of interpreting any model, whether it is linear, it is simple linear or logistic model, look at the p-values. Here we have a star, 1 star here. It means that the intercept is significant. Then we have the weight, which is also significant. We can see a star. The rest of the variables are not significant. What do they mean? What it means is that if you have run a model and then you notice that some variables or some of the dependent variables are not significant, it means they don't have any influence on the model. So in a real life situation, if you are going to produce that model, it means those factors or those variables will not have any impact. They don't either make the model or they don't contribute anything to the model. So you can take those ones out and then look for those that are significant. And so that is what. So when we look at the variables, we looked at the fact that weight has some kind of influence on the model. And then the rest is not significant. That's the first thing you need to do. The second thing is come and check the intercept. The intercept is, we are just looking at this particular value when the rest of the values were not there. If you didn't put any of the values which are there. But not to waste time, I will say that the variable that is significant, here in this case, weight is significant, as you can see the star here, is what we are going to work with. And so how are we going to work with it? You can see that the coefficient of the weight is minus 9 point something. Then once you see a negative sign, it means that even though there is a relationship between the weight and then the transmission type of the car, that particular relationship is negative. It is inverse relationship. It means that whilst the weight is going high, then maybe there's a negative relationship with the output. Now, to be able to calculate or to be able to make sure that you make meaning is you pick the intercept the intercept, which is here, and then you are going to make sure that you pick the rest of the coefficient, multiply them by 1, 1, and add it to the intercept, and your overall results will tell you what you are likely to get. Now, let me come here and then show you what I mean. So I have my intercept, which is 19. Let me put it this way. So I have my 19 here. It's actually 19.70288. Then I have plus 48760. Then I have plus 0.0323259. Then I have the other one should be minus. That's for the weights, because minus 9.14947. And so if we are looking at whether the car type, the transmission type was automatic, then we multiply the coefficient by 1. As you notice that when you multiply anything by 1, it remains the same. So because of that, here I would just run it, and then you see. So what are we likely to get? We are likely to get this particular value over here. Okay. So now we've added the rest of the figures, and then this is what we are getting. So we are getting this particular value, and this is the value we are going to place our interpretation on. Now, if we had plotted this value, we will see that here the value will be closer to somewhere, as against it is closer to 0 or it is closer to 1. And obviously, this is way above 1 or something like that. So this is one of the ways through which we use to be able to interpret our logistic regression. But I just did this for the general view. But you are not supposed to add these two variables over there. You're not supposed to add those ones out. But in the case that the transmission type was a different one, then we would have multiplied each of this by 0. And when we multiply all of them by 0, everything will tend to be 0. And then we are going to have 19. And so it means that our intercept would have been 19. So if the transmission type was, let's say, manual, which is 0, then the intercept is saying that we have 19. And then if the transmission type was, let's say, 1, then we multiply, this is what we would have had. So we now go ahead to interpret based on this word, on whatever we have here. Now, let's look at maybe other things that will make it a little bit much clearer. So this is for like you are modeling more than one variable against one single dependent variable. Now, let's assume that I'm going to pick this out here. I'm just going to copy that out and then bring it down here. Paste it again. And then in this case, let me take the data out. I'll put that 1D. And then I'll come here and say, okay, we noted that the weight was having an influence. So this time around, I am taking the rest of the variables out and leaving only weight. And so in this case, we're just looking at one single value, just one single. And then we come here and look at the summary. We look at the summary of the model. Oh, I'm typing at a different place. I would have just come here to say, look at the summary of the AM dot, and then you run that. Then if you run that, then you pull this out, and then you look at something. So you notice that the weight is now quite significant. And so here we can now, if we now want to be able to check to the response variable, which is the intercept here. The response variable is the intercept here, which is at 12. And then we have minus here. There's still a negative relationship between weight and then the transmission type of the car. So we can multiply this number here by 0 and add to this. And then we are going to get 12. So we can also multiply it by 1 and add to this, and then it's going to slide down. So when it slides down, we can begin to have a specific number, and then we use that particular number to do our interpretation. You can check that out yourself. Now, this is the AIC. AIC is basically used in comparing models, and then we will talk about it when we are looking at ANOVA. So these are various data sets that I have simulated. We can actually check many of the regression type that you can think about. Then you build your data frame here. Here we are looking at obesity, weight, genotype, age, heart disease, sex, admitted, then your GPA. Then we can pick any of them and then begin to look at our logistic regression and how and what that means. Then you can have your outcome, and then you can have your interpretation as well. So, for instance, we could have looked at, there's something here, I could run here, and then come and look at the model summary and see that, and then we realize that, yep, so we are looking at obesity and then weight, and we notice that the two of them, there's no significance. It means that weight did not have any kind of influence on obesity. We didn't see any, it's not significant. And then if you look at the intercept, it's basically, what is it, 0.02. And then if it was like, let's say, significant, maybe we could have worked out and then see where the value is either closer to 1 or it is closer to 0. And then we can interpret like that. So these are the various models that I tried. You can do this over and over. You pause the video and look at it. Now, there's one part of regression that we say to fit the regression model. So what do? We just have the model. So I'm going to run one here. I'm still using the same HP, but this time around, we are looking at horsepower and then the shape of the engine. The shape of the engine, remember that 1 means is a V shape, S means is a straight shape engine. So we print the model summary and then look at something. We'll notice that the two are actually significant. And so we can have the intercept here and the coefficient here to be able to do the interpretation like I explained earlier. Now, there are instances you may want to, like, let's say, after you have fit your model, it's now left onto you to be able to do a prediction. So to predict means the model has been fixed, but you can now choose a new parameter to be able to predict what will happen. So I just created a new variable, just like I showed you guys earlier. Then I come here, I'm now going to do the prediction. And then, of course, if you have done the prediction, we are predicting the model. And then you have your new data, which we have already created a new data, which is here. I'm sure we should remember this. And then go to come here and then try and then print this out. And then you see what we have there. And then we are going to predict. So I'm going to predict the model and then pack it into what we have here. New dat. Let me run this. And then I'm coming to print this out. Okay, and so if I print it, so we have the new model, which is here, and then you can begin to check. I think I've explained some of these things a little bit earlier, just like wasting time. If you check in the multiple linear regression video, I explained it a bit better over there. Then we can plot our logistic regression curve and have a look at it. So if we run this, that's one of it. Then you add a line to it. And then this makes it a little bit easier. So here we are looking at the engine shape, and then we are looking at the horsepower. So if you check, if the car has a horsepower of around 50, that's 50 kilometers per hour, is it likely to be a V-shaped engine or a straight-shaped engine? Come here and follow, then you notice that it's going to be around 1. So it's likely to be a V-shaped engine. So this particular regression curve here is actually moved from the minimum all the way to the maximum, or the opposite. It can be the inverse S shape or the straight F shape, direct S shape. So here we have already seen the inverse relationship, but let's look at something here. You pick up the horsepower value here and check it and see where it corresponds. It corresponds to what? 100% the fact that it's going to be what, a V-shaped engine. What about if you have a car with a horsepower which is around 100 and let's say 130? 130 will be around here. So if you move to this side, you are likely to get 0.5. So there's a 50% chance that it is either a V-shaped engine or it is a straight-shaped engine. That's how you interpret this. If I come here, I have a horsepower of 150. So if I move straight, I'll meet the graph here, go to this side. So it means there is a 0.2 or 20% chance that the car is a V-shaped engine. So if there's a 20% chance that it's a V-shape, then there's an 80% chance that it is a straight car. I know 80% stands taller than 20%. So obviously it is closer to what? 0. And 0 stands for the straight car. So this is how you interpret. If you are not getting how to be able to interpret the actual figures, like I was saying, plot it, and then you are able to get it. And then let me show you how to do the plot. So you have your plot of, you take the, you have your VS. You would have created your new data already, like I have created it on top here. Then you plot your VS, which is your binary data or your response variable, against your independent variable. And then you pick it, you are picking it from this data called mtcast. You just give it a color, it doesn't really matter. And then when you plot that, you are going to have all the figures, you are going to have this dot dot, or what are the zeros, and then this. But what about the proportion? So you add the regression line. So the regression line is the new predictors that you have already created, which is here. Then you come and then you now run it as lines. If you remember, when we were doing the small data visualization, we looked at lines, how to be able to add a line. And so when you take the VS and then against HP, and then we are now plotting it on the new data. It's like this is the model, and then this is the model. The model is the relationship between VS, the shape of the engine against the horsepower. And then we are plotting it on a new data that we have, which is here. And then we are using this particular function called the LWD. We are looking at the direction, and you put 2 there. You can change this figure and see what you are going to get. Well, when you do that, that's where you are going to get this particular plot. So when you are doing your logistics regression, or you are looking at 2 variables, make sure that you create how you fit your model, or you can also come and use this strategy to be able to get your new your graph. Then you can also use the graph to interpret, just like I have shown you how to be able to do it. Sometimes, if I don't want to talk about ggplot now, because that's what I want to use for data visualization, but we could have also used ggplot to be able to plot it, and then we're still going to have the same thing, just like we have it here. You use proportions here, trace it, and then come here. So and what are you going to interpret the results? You will say that if a car has a horsepower of 200 kilometers per hour, is the car like what kind of engine shape is the car likely to have? Then you check your 200 horsepower here, then you correspond here, it's likely to be at 0. So it's a straight car engine. And then you are always looking at these proportionalities, or you are looking at these different proportions which are there that you'll be able to interpret your output. Okay. So quite a number that we are there. But remember, we also looked at some few things here with the distribution. I'm not going to bore you about it. You should know how to be able normal distribution and what it is used for, binomial distribution and what it is used for, and then whatsoever. It's distribution just tell you the skewness of your data, which I explained earlier during our class. But it's not all the time that you have a binary outcome. There are instances you have data and the outcome is a count data. The outcome can be 1, 2, 3, 4. But in any case, the outcome is a count. Okay? Once the outcome is a count, and then the count is more than 2, you are no longer looking at logistics regression, but you are looking at another kinds of regression in which you are looking at the outcome to either be 1, it can be 2, it can be 3, it can be 4. In real life situation, you are looking at an outcome where either the person win, draw, or in a very simple situation, you want to build a model that can predict the number of score line that a particular team is likely to come out with in a match. So there is a match against Asante Kotoko and then let's say Accra House of Oak. And then you want to build a model to be able to predict the number of scores or the number of goals Asante Kotoko will score. And so that kind of model building is not binary. The output or the outcome is not going to be either win or lose. If you are going to build a model that will predict whether Asante Kotoko will lose or win, that is a logistic regression. But if you are going to build a model that you want to find out the number of goals they will score, they can score 10 goals. But in any case, we don't have half goal. They are counts. Okay? And so that's the example that comes to mind. There are some in the health sector that we can look at. If you have an outcome that is more than 2, then it's no longer logistics. It is now called ANOVA. You see? So you do your ANOVA, which is basically the same thing like the regression, logistic regression we're having, but in this case, the outcome is just different. So the ANOVA here, we are still using the same thing. We just do this, and then we come here. We can just create our ANOVA, and this is the function we use for ANOVA. AOV is analysis of variance. So we are predicting miles per gallon, and you realize that miles per gallon is actually, we are looking at the number of gallons per mile based on the horsepower of the car. And here we are interacting it with the car type. That is, either it is an automatic car or it is a manual car. This kind of model building is when you are building a model. Let me use the game again for you to understand. So in this case, we want to build a model that can predict the score line of Asante Kotoko against Aduana Stars. But we are looking at, okay, so the score line is our response variable. Then the match itself or the players themselves is what we are, the individual players efficiency is what we are going to use as our predictor. But in this case, we may want to find out whether it is the short players who will do well, or sorry, it is the forwarders that will do well, or it is the midfield that will do well. You are looking at two things here. So those two things is now our binary data that we want to find out the interaction. Okay, so that is why we have this. So we are looking at the influence of horsepower on the number of gallons a car will consume by traveling 1 kilometer or 1 mile. So that's miles per gallon being explained by horsepower. And the horsepower is also dependent on the transmission type of the car, whether it is automatic or manual. So you are building like three different models. You are building a model of two things that is interacting with a binary output or a binary predictor. And that's what we run here. We use ANOVA to be able to do that. And then when you print it, you have your results, which is here. And you can see the output, which is here. And so you can do that for many. I've tried that in many of them. As you can see, they are all here. But there are also instances you may want to check whether, okay, the forwarders in the football match were those who actually influenced the goals, or it was the attackers who did that. So in that case, or it was a mix between the attackers and then the midfielders whose collective effort made sure that you succeeded in getting the number of goals. So the number of goals is your response variable. Then the efficiency of the players is your predictors. But you are also looking at another two categorical variables, the midfielders and then attackers. Now, when you are using plus, you are looking at their individual effort, or their individual influence on the number of goals that they both, that you scored. But if you are looking at their collective effort, then that's where you use plus. Collective effort, that's where you use multiplication. So you are multiplying the predictor by the independent variable to be able to determine the influence on the response variable. So it's like when you are modeling a disease or some kind of output, and you want to find out whether if it were female, how would they do, or if it were male, how would they perform. The male and the female are the categorical variables there. Then you interact it with the predictor to see what will happen to the response. Again, you could come and pick the predictor separately, pick the categorical variable separately, and see what their individual effect will have on the response variable. And then when you do that, you can just print. So that's what we are doing here. I run the first line, and then that is it. Then you run the second line. And then what you normally would do is, after you have the two the two results which are out, or the two models which are out. So here I call the results 1, that's my model 1, and this is my model 2. What I need to do is to now do ANOVA. ANOVA is when you are now comparing the two models to see which one is better off. Then I come to run ANOVA here, and then you will see which one is better off. Now, if you see that your p-value is greater than 0.5, it means that the interactive model was a bit better, or something like that. And so here we can see that our p-value is 0.9, which is way bigger than 0.05. And so in this case, we can say that maybe the first model was better than the second model. It means that by interaction, the number of goals that were scored, it was because of the collective effort of the midfield and then the attackers, but not their individual effort. So model building is a little bit of a technique that you have to know what you are trying to interact with. I was trying to get an example in the health sector, but I didn't get one quickly. I wanted to see if an instance where we have we are using one predictor on a response based on male and then a female. You see, I was just trying to look at that, but I didn't get that example quickly in my head, and that is it. So this is how we these were some of the things that we discussed earlier in terms of logistic regression, and then the and how to be able to look at their results and interpret them. I'll give further information and maybe ask them when they need be, but for now, just take it very easy like this, and then we can go ahead with that. Thank you.